Okay guys, welcome back to the SSAS training sessions. In last session we discussed about a couple of relationship types between dimensions and the measured groups. So let's say this is your fact table and this is your dimension table, and we discussed about no relationship, that every record in this table will not have any record with relationship with any of the records in the dimension table. So that relationship is called as no relationship. And the second relationship which we discussed is regular. So the regular is more like one to many. One record in the dimension table can have zero to many records in the transaction table. It can be zero also, because there may be some master data which does not have any transaction data. In other words, there may be a product with zero sales. Okay. And the third relationship which we discussed is fact relationship. It is basically one to one. So because both the transaction table, both the fact table and the dimension table is same for the fact relationship. So every record in this one will have self-reference to the record in the same table. So one to one, this will have a reference to this, relationship to this will have relationship with the same, this will have relationship with the same. So this is more like one to one relationship. And we have also seen reference relationship where there will be intermediate dimension tables. Now here in this case, one to many between the transaction table and the first dimension table, or in other words the intermediate dimension table, and one to many from the reference dimension to the intermediate dimension. And let's say if you have one more dimension like subcategory, then one to many to this. So it is more like one subcategory. One category will have multiple multiple subcategories, and one subcategory will have multiple products, and one product will have multiple sales transactions. So we discussed about all this stuff in last session. So in the current session, we're going to discuss about many to many relationship. How the data will be stored in the many to many relationship when two tables or two master tables have many to many relationships. Then we call the relationship between the tables as many to many. Let me show you an example. Let's take our film industry, where we have one hero. Let's say we have multiple hero IDs. If the database of the film industry is maintained, then there will be a master table called actor or hero. Let's say actor, and we'll have a director or movie details in one table. So one actor will have multiple movies related to, like one actor is acted in multiple movies. Similarly, one movie will have multiple actors, right? So this kind of relationship is called many to many relationship. When the two master tables have many to many relationship between these two, then we call it as many to many. And if you take one more example, the books and authors. One book is written by multiple authors, and one author has written multiple books. So if you see one to many from this side to here, and one to many from this side to here, so that kind of relationship is called as many to many relationship. And the third example is cricket. If you take sports, one player will play for multiple teams, and one team will have multiple players. So this kind of relationship is many to many relationship. Let me take an example here and let me show you how the many to many database table looks, and how we can create many to many relationship between the dimensions and the measure groups. So for that, let me take an Excel here just to show you how to define many to many relationship, and how to draw the tables which are many to many in relationship. So first, movie ID and gross collect revenue. Let's say movie ID is 1, gross revenue is, let's say, $100. Movie ID is 2, let's say $200. Movie ID is 3, let's say $300. movie ID is 4, let's say $400. Movie ID is 5, let's say $500. Okay, this is our transaction table. Now let's go with the first master table. So the first master table is actor ID and name. Actor ID is 1, Ramananda. 2, Balai Babu. 3, Chiru. 4, Venki. 5, Nag. And 6, let's say KV, Krishna Bhagwan. So let's say I have this actors information in one of my master table, and let's say the other table contains the movie information. Something like this: movie ID and name. 1, let's say PVC, Paramveer Chakra, and 2, let's say Stalin, and 3, let's say what movies I can think of? Manam, and let's say 4, mm, let's say Shadow. Okay, if you see the relationship between the table here, if you see these two tables, if you ask for the gross revenue of a movie, you can join with this table, the transaction table, and you can view this information. And if you are asked the question like, okay, which actor, what is the gross, like what is the gross of Balakrishna movies, and what is the gross of Chiru movies, and what is the gross of Bengi movies, then you don't have relationship between these two. You can try to set a relationship. Let's assume you have reference relationship. In that case, what we can do, you can have one to many from here, and you can have one to many from here if it is referenced, if the data is one to many in nature. But here in this case, the data is not one to many in nature. Instead, the data is many to many. One movie might have multiple actors, and one actor might have acted in multiple movies. So the relationship between these two master tables here is not one to many, but it's many to many. So in that case, how the database will be designed by the data development team or data architects is like they bring one intermediate table here. So the intermediate table will be like this: actor ID and movie ID. So it's basically the distinct combinations of these two will be brought into this table. Let's say Brahmanandam acted in PVC, and he acted in Stalin, and he acted in Shadow, let's assume. And Balai Babu acted in PVC, and Chiru acted in Stalin, and Venki acted in Shadow, and Nag acted in Manam, and Krishna Bhagwan acted in, let's assume it's PVC, and Stalin, and the Manam, 3, and Shadow. So if you see, I brought one table which we are calling it as intermediate table, okay, or intermediate measure group table. This table will have the distinct combinations of the two master tables here. So when you ask about the gross revenue by a particular actor, let's say Balai Babu, what it will do is it will go here, it will get the ID 2, and it will join with this, and it will get the relevant movie ID. Here is Balaya acted in only one movie, so it will go here and it will get this ID Paramveer Chakra, and it will get the sales of this or gross revenue of this. So this is how you can set the relationship. You can't, as this is not one to many relationship, you can't have either the actor ID here or movie ID here to bring it to the one to many relationship, but the data is but the structure of the data is many to many. So we have to bring in one extra table where we will not be having any metric information, or neither metric information nor textual information. So we call these kind of tables as intermediate tables or bridge tables or factless fact tables. If you see, if you have any design like this, then we can define many-to-many relationships on top of this. So the shortest way of remembering or understanding this one is like one. There should be two dimension tables. This is one, and this is two. And one dimension table, only one dimension table should have relationship to the main fact table. In this case, this is the main fact table where I have metric information, and both the dimensions should have relation. There should be one bridge table, we have that, and both the dimensions should have relationship to the bridge table or factless fact table. So if any database table structure meet these requirements or meet these points, then you can define many-to-many relationship on those tables in order to get the relationship between the fact table and the unrelated dimension table. Like this, here in this case, we can get the relationship between these two with the help of bridge table. In reference relationship, we use the intermediate dimension table to get the relationship between the non-related dimension table and the fact table. But in this case, there is one more extra layer, that is factless fact table, in other words, bridge table. Now, let's see. Let me show you an example in a cube design. So for that, let me take the mouse pointer and let me go to here. And if you see here, this is one dimension table. Can you see? Sales data, where you have sales order number and sales order line number. And this is one dimension table. And this is my fact table. And fact table is related to one of the dimension table. And this is my factless fact table or bridge table where I have only IDs, and this is related to both the dimension table. So if you see, it means all the points are valid in this case, so we can define, right, many-to-many relationship based on this table structure. Okay, so when you have these kind of tables, what you need to do is you need to define the dimensions, and then you need to define the measure group, and then using this factless fact table you need to define one more measure group. So you need to define two measure groups and two dimensions. First, let's start with the dimension designing. So to design the dimensions, let me go here, create a new dimension, and I'm gonna create dimension using the existing table on sales data, and it has composite primary key. That means two columns are combinedly making the table records unique. So I have to select one name column because it has two key columns. So let me show sales order number. Next, let's sales data is fine, and let me bring sales order line number. So this is one dimension. Let me create the other dimension. The other one is sales reason. Let me select the table. Oops, this is not that. Sales reason. Click on next. I need sales reason name, sales reason type. Click on next, and let me name it as sales reason. So click on finish. Now the second step is to make sure whether we have the dimensions, the measure groups. Yeah, the first measure group is added, the main measure group is added. Now we need to define the measure group on the bridge table or factless fact table or intermediate measure group table. So here, normally the intermediate measure group table will not have any metric information, generally speaking, but there could be. If you have a metric information, that's not a crime. You can have the metric information. And if you have the metric information like sales item count here or something like that, you can add it. If you don't have any metric information, generally people don't prefer to have metric information in the intermediate measure group table. So in that case, take the count of rows, and this is one metric, and this metric I'm not gonna use. So what I can do is, whatever name I give, I can go to the properties and I can set the visibility to false so that this will not be shown to the end users. So basically, the intermediate measure group table is used just as a bridge between the dimension tables. It will not be used for analysis purpose. The count here is not going to help us in our analysis. So uh, if there is any metric columns available in this particular intermediate measure group table, then you can add that and you can use it in your analysis. If there is no metric columns, then you can just um, take the count of the rows and hide the count of the rows, because we just need this bridge table in our measure group list to set the relationship between two dimensions. So once it is done, let me add the dimensions that I have added. These two are the dimensions that I've created, sorry. And once I added it, you can see this measure group has direct relationship with these two, and this measure group has relationship with one of the dimension. So this is what I told you. When you have one main measure group and one bridge table and two dimension tables, then when both the dimension tables are related to the factless fact table or the bridge table, and any one, either this or this, is related to the fact table, then we can set the relationship indirectly to the other dimension and the main measure group table. So here, now if you see, the fact table, the factless fact table and the dimensions are related. This is the case. And one of the dimension, that is sales data, is related to the main fact table. Now the missing one is the sales reason. The sales reason is missing, and you can use many-to-many relationship to define the relationship between sales reason dimension and fact internet sales. Let's quickly see how we can set the many-to-many relationship. It's pretty simple. You just need to go here, many-to-many, and it will ask for the intermediate measure group here. In the reference relationship, it asks for intermediate dimension, but here it's intermediate measure group. If you select it, and that's it. So the many-to-many relationship is set. Now if you try to query sales reason and the fact internet sales, it will come here and it will join here, it will join to this, it will join to this, and it will get this information from here. So this is how you can set the many-to-many relationship in this case. And let's assume there is no relationship between let's say this one. Okay, now the many-to-many relationship will fail. This will not work because there is no relationship between these two. And if here you can see the relationship cannot be defined because no intermediate measure group or dimension table exists. If I go here, it won't show that. The main criteria is when you want to use any measure group as intermediate measure group for many-to-many relationship, then it should have relationship to that dimension, and it should have relationship to any other dimension where even this one has relationship. If product key is related, then fine, you can use this many-to-many, or customer key, fine, or product subcategory is fine, or this is fine. So two dimensions should be related to the bridge table, and one dimension from the two should be related to the fact table. Then only you can use the remaining dimension for setting the many-to-many relationships. And let me give the relationship back, and if I select the sales order number, this is a composite key. Yesterday we were discussing, right, how it shows. Here you can see it is showing two columns. You need to select mapping for two columns, something like this. Once it is done, then if you come here, it will show the intermediate measure group table, and click on OK. This will build the many-to-many relationship between the sales reason and the fact internet sales. Now let me quickly process, and let me show you how the data looks, or how the data will be fetched when you pull a record from the sales reason dimension and the fact internet sales metrics. So let me process it. It should not take more time. Okay, it is done. Browser. So let me take sales amount, tax amount, and sales reason. Now you can see the data is splitting based on the main. This is related to the fact internet sales through many-to-many relationship, and this is how you can see the data. The data will be split, aggregated, and it will be shown in the result set. So this is about the many-to-many relationship and the last relationship in our analysis services in our discussions. Like the other one is mining model, so which is not part of this sessions. So we'll not be discussing about mining model type of relationship. Now we have seen about the dimensions, how to create dimensions, the measure groups, and also how can you, what kind of relationship you can give between, you can define between the dimensions and the measure groups based on how the data is related in your underlying database. Now let's see one of the important interview questions, that is types of dimensions. Basically there are these following types of dimensions. One is degenerated dimension, another one is junk dimension. This is degenerated. The second one is chunk. Third one is conformed dimensions, CONFORMED, conformed dimensions. And fourth one is role playing dimensions. These two sounds like same. When I explain about these two sounds like same, and these two sounds like same, but these four are different types of dimensions in analysis services. Let's start with the degenerated dimensions. The best example for the degenerated dimensions is something that we have just seen here. If you go to the data source view, this fact internet sales reason, no, the sales data is nothing but the table, a dimension table that has been created by using fact internet sales table. If I go to the name query of this, you can see the source for this dimension table is nothing but a fact table. You can see fact internet sales. It's built on fact internet sales. I know the sales order number and sales order line number combinedly will form the uniqueness, will form the primary key for this table. And user want to see revision number and career tracking number and customer PO number. So I have these columns and I create it. So when the fact table, when the dimension table is derived from the fact table, then we call such kind of tables as degenerated dimensions. So here in this case, the sales data is nothing but the fact table information. The source for this sales data is the fact table, and we're using it for creating a dimension. Why we need to create a dimension based on fact table? It is not advisable because normally fact table means it's the biggest table. Normally in normal case. Uh, Generally, a fact table will have some thousand millions of records or even more than that, the biggest fact tables. So why you need to create a dimension table on top of it? Sometimes users want to see what is the order number or what is the shipment ID number or something like that. In that case, every transaction record will be having one order number. The dimension table that is derived from the fact table will be almost same number of records in this case. If this has 1 million records, this will have very close to 1 million records. That when we have that kind of data, and if it is requested by the users for using it as dimension, then we need to create a dimension on top of that. When the fact table loses its, and degenerates and become a dimension table, we call it as degenerated dimension table. Okay, here the fact table, on top of it we are trying to create one dimension table and using it for creating the dimensions. When you have this kind of scenario, we call it as degenerated dimensions. In degenerated dimensions, the cardinality means the number of rows, matching rows here. One row here will be one row here or something like that. It will be very high, like let's say there are 10 million records in your fact table. The dimension table which is created to create the degenerated dimension will have almost same number of records. So the problem with this one is the storage, data storage. Assume this is my fact table and it has 1,000 million records, and you know how big the table is. And let's say this is my dimension table which I pulled or created on top of the fact table and to create a degenerated dimension, and it has almost same number of records, let's say 900 or 1,000 million records. So in this case, if you create a dimension on top of it, it will be very huge. Okay, it will be very difficult to create a dimension, and it takes a lot of time to process, and it occupies a lot of storage because it has a lot of data, right? And mainly the cardinality issue. That is why people don't prefer to have these degenerated dimensions. If the requirement is there by, I mean, if it is requested by the users, then we don't have any other option of other than creating the degenerated dimensions. But in real, people don't prefer to have this one-to-one relationship kind of tables to be used as a dimension table. One-to-one relationship with the fact, this is really big one. If you see, this has 1 million records, then this will be having close to 1 million records. This has 10 million, this will be close to having 10 million. If you see the sales order number and sales order line number, this will be almost unique if you compare with the fact table here. So the mapping will be like one to one, and the table size, the dimension table size, the sales data size will grow with the fact internet sales table, and hence it occupies a lot of memory. The processing time will be more for this dimension. Sorry, not lot of memory, lot of space, and the processing time will be more, and the cardinality is very high, and it can't be used for filtering and all. It can be used only for displaying purpose. Like if the user selected a particular order details, then the data from this, let's say sales order number or sales order line number, can be used to display in the charts. So when you have dimension created on top of a fact table with high cardinality, low cardinality, which means it has almost same mapping records, then we call it as degenerated dimensions. On the other hand, when the dimension table is built on fact table, let's say one more, with um, very less number of combinations. For example, let me take Excel here. Oops, sorry. So let me take Excel sheet and let me go to the sheet 2. So let's say I have a fact table, the fact ID or no ID, let's say product ID, customer ID, salesperson ID, and sales amount, tax amount. And let's say we have something flags like this: is shipped, is ordered, is delivered, is due cleared. So if you see something like this, these kind of flags will be maintained in the fact tables. When you have these kind of flags, okay, basically it will be like yes, yes, or they may be using bit like 0 and 1. 0 means no and 1 means yes, or they may be using true or false boolean values. So let's say yes and no, and let's say this is yes and this is yes and this is yes and this is yes and this is no, 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 something like this. When you have a data like this, when you have a lot of flag information, true or false, in your fact table, this may be required for user analysis in few cases. For example, user want to see all the product sales which are shipped, so you need to get only yes for shipped, correct? All the orders that are delivered, you need to get all the S for the delivered. So it'll be very difficult if you have this information in your fact table and if you create a measure group on top of this. So what people will do is they'll just take this out of this table and they'll create another dimension table, and they'll be having a flag ID, something like this, a unique ID, 1, 2, 3, and the unique combinations will be stored in the fact table, in the dimension table, and here they'll be maintaining the referenced flag ID. So that means one flag ID let's say I have one here, that means this particular transaction is shipped and ordered and delivered and due not cleared. If I use 2, this will be mapped like this. This dimension and the fact table is mapped using the flag ID. So instead of maintaining the flag information in every fact record, we are taking the distinct combinations. Yes, 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 no. Yes, 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 yes. Yes, yes, no, no. Yes, no, no, no. No, 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 no. Something like that. All the distinct combinations will be brought into one dimension table, and we'll be using those IDs in the fact table. So this dimension table is created on top of the fact table, right? So similar to the degenerated dimension, but if you see, the cardinality is entirely different. There you'll be having lots of combinations, one-to-one relationship, very close to that. Here, hardly for 100 million records or 1000 million records or 1 lakh million records, you'll be getting hardly the distinct combinations. Let's say 60 records or 50 records or max 100 records. So there is a distinct combination of these four, and this ID will be used on instead, right? So we will be creating one dimension on top of this, and we call it as junk dimension. The junk dimension is basically like moving all the junk columns from the fact table into the dimension table to create a dimension. What is meant by junk columns here? Something like flags, which can be used for filtering purpose, basically in the metadata. Um, Sorry, in the dashboards. If you see, if I created one dimension on top of these four columns of this dimension table, then if user selected is shipped attribute and selected the value s, then it will take all the combination flag IDs which has s for e shipped, and these IDs will be matched here, and the mapping records will be fetched, and the sales amount of that will be fetched and displayed. So the sales amount is only for the products which has been shipped. So something like that. So you are creating a dimension using the flags or the junk columns from the fact table, which is not useful as a measure, but users can use it as a dimension to filter the data in the dashboards. We call these kind of reports as junk dimensions. And if you see, the degenerated dimensions cardinality and this cardinality is entirely opposite, and the storage wise, the degenerated dimension takes more storage, whereas this one takes less storage, and this is easy to process, less time to process, and the other one is more time to process. And degenerated is mainly used for displaying the values in the reports, whereas this is for filtering the data in the dashboards. So this is the major differences between degenerated and junk dimensions. Both same sounds similar, like creating from the fact data or the junk data, but there is a lot of difference between these two. Now let's see the next type of dimension, that is conformal dimension. The conformal dimension is basically when a dimension acts the same way when it is related to two fact tables. So to talk about the conformal dimensions, you need to have two measure group tables at least. Okay, so this will have relationship to this and this will have relationship to this, and it behaves the same way to the two measure group tables. The best example is date time. If you take date time here, okay, then this is same datetime, it acts as a datetime, and the data will be same if you join and if you see the data with fact internet sales measure group or factory seller sales measure group. So the most common example for this one is datetime, and the dimension which acts the same way for multiple measure groups, we call it as conformal dimension. So let's try to create one conformal dimension in our cube, and let's see how it works and what's the advantages of having a conformal dimension. And while designing analysis service cubes, try to make sure that you have a good number of conformal dimensions. That really helps the cube designing. So here, as I said, I need to have at least two measure groups, and let me add one more measure group here. I will try to add reseller sales, okay, and I'll try to add freight amount, okay. And if you go to the dimension usage, it's already related. The product acts the same way for the internet sales and the reseller sales, and it set the relationship and the category and the subcategory too. Now What is the advantage of having the confirmed dimension? By default, it will take the relationships because it is defined in the data source view. And what is the advantage of having the relationship, having a confirmed dimension in analysis services? Let me process this and let me quickly show you the output and what's the advantage. So basically, these confirmed dimensions brings relationship between two measure groups. Okay, so if there are two measure groups and if you want to bring the relationship between these two and if you want to analyze the metric information from two measure groups, then the conformal dimensions is the best to go ahead with. Now fact internet sales has sales amount and tax amount metrics, and this has freight amount, and product acts as my conformal dimension, right? Let me go to the browser. Okay, let me reconnect it, and I'm taking sales amount from here and freight amount from the other measure group. And if I try to take the customer which is not a conformal dimension, let me take the first name, and you can see it is filtering only the sales amount, but the freight amount it is showing the duplicate value or the total freight amount repeating for every first name. So this is not the best result set that users will be expecting. So users want, when they want to analyze the sales amount and the freight amount from two different measure groups based on one attribute information, then you need to have a conformal dimension on top of this. Now let's see the product. If I drag and drop the color, you can see when the color black has sales of 88 something blah blah blah, the freight amount is so and so 734943.1229. So these two measure groups, if you see this measure is from one measure group and this measure is from one measure group, these two are having relationship and user can able to analyze these two measure group data based on one dimensionality or based on multiple dimensionality if it has conformal dimensions defined. Now let me go to the product category, English product category name, and even you can see here even this is filtering properly because this is also a conformal dimension. It has relationship to both the measure groups and it acts the same way. The product category acts the same way for reseller sales as well as internet sales. And let's say you have a date wise sales amount and freight amount, you can see when you have the conformal dimensions defined on top of these two measure groups. So this is about the conformal dimensions. In short, when a dimension acts the same way for the two measure groups, then or two or more measure groups, then we call it as conformal dimensions, and you can have a number of dimensions defined like this. So but make sure the data is proper in the dimensions and the measure group tables, and just for the sake of creating conformal dimensions, don't give junk relationship. Give relationship only when the data is related. So this is about the conformal dimensions, whereas the role-playing dimensions is slightly different. So the role-playing dimensions is more like one dimension in the database level. So this is a database level dimensions. One dimension here will play multiple roles. Let me create a new cube to demonstrate the same because there are a lot of dimensions and measure groups already in my existing cube. I'm creating an empty one on top of AdventureWorks DW. I'll give it as role-playing dimensions sample. Click on finish and an empty cube is created. First, let me create a measure by using fact internet sales here, and let me go with sales amount, and here I'm adding before that let me check whether the data source is defined properly or not, if there is anything missing. Now I'm just refreshing. Okay, I think I played with the data source view. I'm just making sure that everything is in sync with the underlying database. Now let me go to the cubes. Now it is in sync. And let me add the date dimension. Date dimension is only one that is defined in the database level, right? The database dimension level is this one, and this is cube dimension level. So for the cube dimensions, I'm adding the date, and if I click on date, you can see one single date dimension is playing multiple roles. One is as order date, one is as due date, and one is as ship date. So The role-playing dimensions is like the dimension, one single dimension in the database dimensions level will play multiple roles in cube level, cube dimensions level. So we call such kind of dimensions as role-playing dimensions. So the difference between role-playing dimensions and the conformal dimensions is, if you go to the conformal dimensions, okay, and here it is. So here there will be only one dimension at cube dimension level, but it will be joining to two measure groups. So the dimension at the cube level is only one, and it will be joining to multiple measure groups. Whereas if you come for this, the role playing dimensions, it's slightly different. Here you will have only one dimension defined in the database level, but it will be playing multiple roles in the cube, but all these things will be pointing to only one measure group. It's not for the multiple measure group. So this is the difference between the role playing dimensions and conformal dimensions, and why and how it created three dimensions at cube level when I added only one. It is purely based on the relationships that you have defined in the data source. If you see between the fact internet sales and dim date, you have three relationships defined. Let me arrange the tables first. And fact internet sales is here and dim date is here, and you can see it has three relationships defined, right? And what it will do is it will set the relationship, and it will take this relationship and it will create the dimensions, and it will rename the dimensions, and it will give the relationship between these two. And if you see here, if you go to the properties of the first dimension, you can see it is the name is order date, but the base dimension will be, let me expand this, the properties window, and order date, and the base dimension or the root dimension is dim date, and for the due date is the same. The name is just, this is an alias name at the cube level. The underlying dimension is still dim date. Similarly for ship date, the underlying dimension is ship date, or the database level dimension is ship date, but the alias name at the cube level is ship date. And if you see here, it will set the relationships to the order date is related to order date key. Here you can see the measure group table, it related to order date key, and due date is related to due date key, and ship date is related to ship date key. So this is why if you define the data source view properly, then all these works will be taken care by analysis services. And let's assume you have not defined it properly in your data source view. Let's say there is no relationship defined, and this date is role playing dimension and it has multiple options. I mean, it can play multiple roles in your cube by joining with the date, order date, and due date and ship date. Then how you can do that manually without the help of analysis services? I mean to say that how you can create role playing dimensions without the help of analysis services. Now that if I try to add the same dimension dim date, only one dimension is added. The reason being the relationships has been removed from the data source view. Now how can you do that? To do the same, you need to rename it, or better you go to the properties and you can see the name of it. You can name it as ship date. So the first one is created, and add the same dimension once again. Go to the properties. I'll name it as due date, and add one more time the same dimension, and name it as ship date, right? Ship date, due date, and order date. So I created three copies of the same dimension. The next job I have to do is to give the relationship. So all these are directly related as per the database design. So let me go to the regular relationship, and the dimension granularity will remain the same, date key for everything, but what column you will be joining in the measure group plays the major role here. So this is for ship date, so I'll join with ship date key, and this is for due date. I'll take the same granular attribute and I'll join with due date key, because it is for due date dimension, due date cube dimension. And the third one is for order date. So I'll take order date key. So now the advantage of the role playing dimensions is you'll be having only one dimension at the database level, but you will be, as you can see, it is playing multiple roles in the cube, right? Now let's say you can do it in a different way. You can create three dimensions here with a different name, one with order date, one with ship date, and one with due date, and you can add these three to your cube, and relationships can be given. But the problem is you will end up with the three dimensions at the database level. That means here, and it has to process three times. But in this case, it will be processed only one time, and it will be used with three different images or three different copies with three different roles. So that is the major advantage. The processing time will be reduced, and the number of dimensions it has to process is reduced. If that is why people prefer to use role playing dimensions, and it's a very easy and very useful option in analysis services. So the only thing that you have to do properly is the setting up the relationships in the data source. If you set up the relationships, then it will take the headache of adding the dimensions with different names to the cube and setting up the relationships between the measure group table and the dimension tables. So these are the four different types of dimensions. One is degenerated dimension, which is degenerated from the fact table and become a dimension table. Another one is junk table, junk dimension, which is nothing but all the junk columns, like all the flags from the fact table, will be pushed into one separate dimension table. And the third one is confirmed dimension, where the dimension is playing or acts similar or acts the same way with the two or multiple measure groups, two or more measure groups. We call it as confirmed dimensions. And the fourth one is role playing dimensions, in which the one database dimension will play multiple roles when it is added to the cube. And for last two, the date dimension is the best example. And for the first two, the first one it's like sales order number, and the second one, the junk dimension, it's the flags. You can take any flags and explain as an example. So this is about the different types of dimensions, and this is all what I have for this session, and we'll catch up in the next session with the different tab options here, like calculations, KPIs, actions, partitions, aggregations, perspectives, and translations. Catch you in next video. Till then, bye bye.